Okay, so we left off with these formulas for reducing powers last time, and I think I was in a little bit of a hurry and I forgot to talk about where these formulas actually come from. So if you look at these double angle formulas here, and in particular look at cosine 2 theta equals 1 minus 2 sine squared theta, and then the other one 2 cosine squared theta minus 1. If you solve this one for sine squared theta, you'll get this formula. And if you solve this one for cosine squared theta, you get this formula. Notice you add the 1 and then divide by 2. So really these are just rewriting these two formulas. And then for tangent squared, you just take this divided by this and you get this. So just so you see where they come from, but they do basically all these formulas that we're talking about in this section can be derived from the previous set. Well, not all of them, excuse me, but derived from some other formulas or identities that we're working with. So the half angle formulas, the next set, are actually derived from these formulas here. Notice the square here. If you take the square root of both sides on these, you would get plus or minus because there's two solutions, and then the radical. And then if you compare the x here to the 2x, this is double this. So we just replace this with a, let me say that again. This 2x is double this, or in other words, this is half of 2x. So if you compare the pattern, this is half of x. So it's just using a different expression to denote the same relationship between those two numbers. This number is half of this one. So these half angle formulas are derived from these formulas for reducing powers. Okay, so the half angle formulas, we can use these in much the same way we use the double angle formulas, and that is to find the exact value of an angle or a number that we don't have, that doesn't correspond to a special angle or a special number, right? It's not one of those special points on the unit circle. So in the first one, 22.5, we can see that's half of 45 degrees. So this will equal, so what we want to do is, this should be the special angle here, or number, right? Whatever is up here will go into here. So if we write this as 45 degrees over 2, right, 22.5 degrees equals 45 degrees over 2, then we can plug it into this formula. Now, notice in these two formulas, and I'm going to erase that here. You can write it down, or I'll put that arrow back in a second. The plus or minus in the formulas, all three of the formulas, these signs are determined. You need to pick those, okay? You don't just leave that. They're determined by the quadrant that this number is in, and that's x over 2. So we are finding the cosine of 22.5 degrees. This is in quadrant 1. So of course this has to have a positive value, right? So you pick, is it positive or is it negative? And this is positive because that's in quadrant 1. So when you plug this in, the 1 minus cosine x, right? So this x is our special angle. That goes here. And then it gives us something that we can evaluate exactly. So this is 1 minus, so this 45 degrees goes in here. 1 minus cosine of 45 degrees over 2, all under the radical. And again, you would give this the sign. You have to decide whether it's positive or negative. Positive in this case. So now we can drop the plus sign. We don't need to write that down. 1 minus the square root of 2 over 2 divided by 2. That's not simplified, so we need to simplify that. So what we do, we can just do this under the radical. We want to clear this fraction on the in the numerator, so we'll multiply by 2 on the top and then 2 on the bottom. Now really we're that's the square root of 2 over the square root of 2 because it's all under the radical. So then it's the square root of, distribute the 2 minus the square root of 2 in the numerator, make sure you take 2 times both terms, all over 4, and then that's the square root of 2 minus square root of 2 over 4. So this would be the exact value. It's not a nice looking number. Notice it's got a radical under a radical. It's called a nested radical, or a nested square root in this case. You can't simplify that. You have to leave that. But again, with your calculator, you can plug it in and show that you have the right answer. So at least if you're taking the test, you can feel better about your answer, that you have the right number. Because we can easily put in cosine of 22.5 degrees. Check, I'm in radians, so I need to change to degrees. Right? So cosine of 22.5 is 0.9238, etc. So when I plug this in, I should get the same number. So square root of 2 minus the square root of 2, and then close that off, so that's this set of parentheses here gives us, we're taking the square root of all that. Hopefully you get, maybe, let me try the light. There, that's a little better. Hopefully the glare doesn't get bad. So you see that parenthesis, 2 minus the square root of 2 inside. And then divide that result by 4. Whoops! And it's wrong. Good thing I checked, because I forgot to take the square root of 4. This should be a 2. So go back to that and change that to a 2. And it's still wrong. What did I do? Good thing I checked my work here. I have a mistake. Cosine 2 over 2, 4, 2 minus square root of 2, 4, 2. What did I do? I see what I did. See, this is why it would be better to have a class in the same room as me. What did I do? I used the wrong plus. So I have a choice. I can stop the video and start over, or I can just admit I made a mistake and be happy I checked my answer, which is what I'm going to do instead of starting all the way over. So let's try it again. These should all be a plus. I make mistakes too. No, I was just looking. So these formulas here, I don't make you memorize them because I find it hard to remember which one is plus and which one is minus. I have to look them up myself, and I looked in the wrong spot. Okay, so back to my number. Let's try it one more time. This time with a plus. Okay, well that's a good example of why you want to check with the calculator. Now I can see that is, I lost my cosine value, but cosine of 22.5. Now I know for sure I have the right answer. So with that minus, that would have been the sine of 22.5. Right? Then there's the 3.826. Okay? So you can see the formulas work here if you have the correct formula. All right. Good thing I checked that one. So we'll check B as well. Make sure we get the right formula this time. So 5 pi over 12, that's not a special number, but if we think of it as half of a special number, then we can use this half angle formula. So this is equal to, so note, let's put it here. 5 pi over 12 is equal to 5 pi over 6 times a half. So if we take this 5 pi over, write this as 5 pi over 6 over, what am I doing here? Over 2. Yeah. So, sorry, I lost my train of thought. So you're taking, if you want to divide by 2, you multiply by a half. I should have said that right here. Right, this is divided by 2. So 5 pi over 6 divided by 2 is 5 pi over 12. This is a special number because it has a reference number of pi over 6. So now we can find this exactly. So this time using the sine formula. Now when we do this determine the sign, plus or minus, we look at the 5 pi over 12. That's in quadrant 1. Okay, we don't look at the 5 pi over 6 because we're trying to find the sign of this number. So we look at this, not this, right? Now sine is positive for both, but if this were cosine, that would be, 5 pi over 6 cosine is negative, then if you put a negative there, you'll have the wrong number. So make sure you're looking at the original number before you made it into a half. Okay, so then the sine is 1 minus cosine of 5 pi over 6. So this number here is what goes in here. Sometimes people mess that up. They're confused what actually goes in that spot. And then divide by 2. Okay, so this time I have the right formula. Sine has the minus sign. Otherwise the formulas look exactly the same, so it's easy to get those mixed up. Alright, so now we've got the square root of 1 minus cosine of 5 pi over 6 is negative square root of 3 over 2. So here is where that negative comes in. And that's important. If you miss that, you're going to have the wrong answer. Alright, so now we have the square root of 1 plus square root of 3 over 2 over 2. And then we want, again, this is not considered simplified. This is all under the radical, so just under the radical multiply by 2 over 2 to get rid of this half in the numerator. So now we've got the square root of 2 plus the square root of 3 over 4. And so that's the square root of 2 plus the square root of 3 all over 2. So let's double check now. This time make sure we have radians. So go here. Sine 5 pi divided by 12. So 0.9659. That number looks familiar, doesn't it? Wasn't that? Well, whatever. I can't remember exactly. Can't remember everything. So 2 plus square root of 3, like so. Make sure you get the parentheses right. Divided by 2. We got the right answer. So this time I didn't mess up. So you can use your calculator to check your work. Now again, I don't want this answer for the answer, right? I want the exact value. This is it here, but you at least, now we know we have the right answer. Okay. So let's, what do I got here? A couple of identities, and we're going to use the, what was I thinking when I wrote this here? The first one, well, let's actually do the second one first. That one's easier. So the tangent of alpha over 2, let's use this formula here. And I didn't really talk about the tangent formula. With the tangent formulas, you can always use sine over cosine to get the formula. So notice if you take this divided by this, you get this. But then it can also be proven that this is equivalent to one of these two expressions. I'm not going to prove that, but you can show this equals this. But with the tangent, usually you just use one of these here. Or you already find sine and cosine, so you can just divide and tangent. That's the easiest thing to do with that formula. All right, so let's go back to the identities. Sorry, I got sidetracked there. So we're going to start with, clearly we need to, on B here, somehow get from a half angle to a full angle. So let's start there. So we're going to use a half angle formula. And clearly we need to use a tangent formula. So we can use this form, or this form. We need to pick the one that looks the most similar to where we want to go. And in this problem here, we've got one term on top and two in the bottom. So that probably, you know, gives you enough of a clue that you want to pick this form here. So that's what I'm going to do. So I'm going to start with the left-hand side, which is tangent of alpha over 2, and then use the identity, but replace the x's with alpha. So it is equal to the sine of alpha over 1 plus the cosine of alpha. And again, that's just from here. I just used alphas instead of x. Okay, let me turn my page a little. So back here, now can I get this from this? So notice secant is 1 over cosine 1. So if I did 1 over cosine, and then cosine over cosine would be 1, and sine over cosine is tangent. So what I need to do is take the numerator times 1 over cosine alpha and the denominator times that same expression, right? So then this is a unit fraction here, and we're not changing the value of the expression. Okay, so sine alpha times 1 minus cosine alpha is tangent alpha. Well, let me put this extra step in here maybe. We could go straight to the final result, but let's write this step in. So sine alpha over cosine alpha over, and then this will get distributed through 1 over cosine alpha plus cosine alpha over cosine alpha. So we got tangent alpha over secant alpha plus 1, and that's what we wanted to prove, right? So we go from here to here and so forth. I don't know why I have this one second, because this one is a lot easier than the first one. The first one, we need to use the sum formula, which, sorry, where's my notes here? That's in the previous section. I'm just wondering. Oh, but we're gonna end up using the double angle formula. I was just wondering why I put this one in this section, but we're gonna need this formula too. But before we can get a double angle, we need to, sorry, so let's start with sine 3 theta. I should have looked at this before I started. So if you take the 3 theta and write that as 2 theta plus theta, so then you have a sum of a single angle and a double angle. And then use the formula for the sum, the sine formula for sum, or the addition formula for sine, in other words. So you get sine of 2 theta cosine of theta plus cosine of 2 theta sine theta. So that, I don't have those notes handy, I don't think, but that was from section 7.4 that I got that formula, right? So now we can use the double angle formulas here. And, this sine of 2 theta, well, let's look at where we want to end up. Notice all of these are in terms of sine. So let's, but they're all sine of the single angle, so we need to get this double angle out of here. The only formula we have for sine of 2 theta is that's equal to 2 sine theta cosine theta. So let's start there, and then we have this cosine theta. Just bring that over here, plus, and then here we have another double angle. We want to get rid of that. Because we want everything in terms of sine, hopefully you're thinking about, because there's 3 versions of that, right? Hopefully you're thinking about this one, because that's the one that has only sine in it and not cosine. So let's replace cosine of 2 theta with 1 minus 2 sine squared theta. Okay, and then we still have this sine theta here. Right, so this is this part, and then this is this part. So we've got 2 sine theta cosine squared theta plus, and then we have sine theta minus 2 sine cubed theta. And this is nice here, I think, because I'm seeing a cubed in here, so we're maybe on the right track. So we need to get this all in terms of sine. So now we want to replace this cosine squared theta with sine theta, and of course the identity that relates cosine squared with sine is sine squared theta plus cosine squared theta equals 1. So of course cosine squared theta is 1 minus sine squared theta. So now we have 2 sine theta minus 2 sine cubed theta plus sine theta minus 2 sine cubed theta. And now we have actually what we need, because notice 2 sine theta plus sine theta is 3 sine theta minus 2 sine cubed theta minus 2 sine cubed theta is minus 4 sine cubed theta. Whoops, that's a proof, so I don't want to circle that. Our answer is the whole thing, right? The proof is what we need here. All right, so that was a harder one. We had to use a whole bunch of identities. We used the Pythagorean identity. We used the addition formula for sine. We used the double angle formula for sine and the double angle formula for cosine. And then we used the Pythagorean identity. So that one is, that's a challenge one. Definitely this one is the easier of the two. I should swap those. All right, well, let's move on. We have 2 more sets to do, and these ones, we don't use these ones as often as the others. So, but let's just state them so if you need to do this. So this first set here, we take, they're called product to sum formulas because you take a product of sine and cosine, and it becomes a sum, excuse me. And these two are pretty much interchangeable because notice they both have sine times cosine, right? So you can just, if you have sine times cosine, you can write it as cosine times sine because multiplication is commutative, and so you could use either formula. So there's 2 equivalent statements there. But they look different, right? So let's see what my examples are. Oh, I got cosine. Okay. Well, we won't do that then. So cosine, there's only one formula for that, and sine, there's one formula for that. So using u and v, but you can use other variables. Whatever these are, you add them here, subtract them here. All right. We'll talk. We're gonna prove. Oh, let's see. I should have looked this over ahead of time. I'm sorry, I can't remember what I'll have here. We're going to prove the cosine formula. When you prove this, I'm going to switch to a pen. That pencil's dull. When you prove this, it's you want to start with this side because we don't know there's nothing really to do there. We don't know anything about that other than it equals this, but that's what we're trying to prove. So we're going to start with the right-hand side and use the sum formula for cosine and the difference formula for cosine. So 1/2 times cosine of u plus v is cosine u cosine v minus sine u sine v plus, so that's this part, right? Now we're going to do cosine u minus v, so that's cosine u cosine v minus sine, plus sine u sine v. And so notice what happens. These add up to 0. They cancel. They're the same thing, add plus and minus. And then there's 2 of these. So we got 1/2 times 2 cosine u cosine v. But 1/2 times 2 is 1. So we got cosine u cosine v. All right. So now, you know, that just proves one of them. The other 3 are proven pretty much the same way. Just use the appropriate sum or difference formula. I have this example here. So here we have a product. We're going to express it as a difference. Actually, we can do what I was saying before. Notice that this one follows this pattern, but this is also equal to sine alpha cosine 3 alpha. So you could use this one, you just change your perspective of what the first number is and what the second number is, right? So I'll do it this way first, and then I'll show you the other way. Okay, so cosine 3 alpha, sine alpha, we're going to use, again, you don't need to memorize these. They're so similar, it's really easy to get them confused. So I'll provide these on the midterm. So 1/2 times the sine of u plus v. So again, think of it more as first plus second. So 3 alpha plus alpha minus sine of u minus v, so first minus second, 3 alpha minus alpha. So we get 1/2 times sine of 4 alpha minus the sine of 2 alpha. And that's our answer. So we're taking the product and getting a sum. Again, this is something we would need to do more in calculus, so we're just kind of getting you prepared for that. Like, really, why do I want to do that? Well, right now there's really doesn't feel like any point other than just practicing using a formula. Okay, so if we change our perspective and call it sine alpha times cosine of 3 alpha, that's still equal, right? We just reordered the factors. So now we would use this formula. We get 1/2 times the sine of alpha plus 3 alpha is 4 alpha plus the sine of alpha minus 3 alpha. I should have wrote down alpha plus 3 alpha in there, but that's 4 alpha. So see what happens. So you get sine of 4 alpha. Remove that. It looks different, but notice that this is negative 2 alpha. And because sine is an odd function, the negative can get pulled out front, and we end up with the same result as above. So those formulas, you could use either one. You just reorder the factors, right? So from here to here, that's because sine is an odd function. If this were cosine of negative 2 alpha, cosine's even, so that would be equal to cosine of 2 alpha, and this would, of course, stay the same. All right, so that's the only type of problem I'd have you do with the cosine, or excuse me, the product to sum formulas for cosine and sine. Sorry, I'm getting tired. All right, so one more set, and that is the sum to product. So we're going the reverse, and these sum to product formulas can be derived using the product to sum. You just do some variable changes, and you will get just rewriting the formula. So this is when you want to go the opposite direction. You have a sum or a difference like in here, and you want to create a product. And these ones are nice if you're solving an equation, because we like to be able to factor. Like on this one, we really don't know how to solve that unless we can get a product. So going from a sum to a product is handy. So we will just apply this here. Use one of the formulas. So you just look for the pattern. This is sine minus sine, so we'll use number 2. We want to write that as a product. So again, think of this as first and second, and so you're just adding or subtracting. So sine of 4t minus sine of 5t equals 2 cosine of 4t plus 5t over 2 times the sine of 4t minus 5t over 2. So we get 2 cosine of 9t over 2, or 9/2 t, times the sine. So notice this equals negative t over 2, or negative 1/2. Let's move that over, negative 1/2 t. Because sine is odd, we want to simplify that and bring the negative out front. So I'm just going to put 1/2 t, and then the negative comes out here. I'll just make this equal sign a negative and then put my equal sign over. So that's negative. So again, that negative is from this here. Sine of negative t over 2 equals negative sine of t over 2, or 1/2 t. All right, let's go on to the next one. Here we're going to basically do the same thing, but we're going to solve an equation. So we want to take this difference and write it as a product. Obviously for this one we have to use formula 4. Again, you don't have to memorize these. They're just, we don't use them that much, and they're really, a lot looks the same, so it's just too much memorizing for something that we don't use that often. So cosine 6x minus cosine 2x, that is equal, I'm just going to go right here, to negative 2 sine of, so we see we take 6x plus 2x is 8x over 2 times the sine of 6x minus 2x is 4x over 2. That equals 0. So negative 2 sine 4x sine 2x equals 0. And I didn't say what type of solutions, so then we would assume we want all solutions, right? We can divide the negative 2 out of there, divide both sides by negative 2, and basically just set each of these factors to 0. So sine of 4x equals 0, or sine 2x equals 0. So the first one, x would be equal to, so on the unit circle, sine is 0 at 0 and pi. Those are pi apart, so we'd say 0 plus pi k, or just pi k, or you can use n, like in the homework, right? You can use an n. But that's actually 4x, excuse me. And then divide both sides by 4, so x is pi over 4k. That's our first set of solutions. And then this one, 2x would equal pi k, so again 0. So that implies x equals pi over 2k. There's our other solutions. So you need both, all of those to get all solutions, and for these k is a real number. Or, no, it's not. It's an integer. Sorry. Which is a real number, but we want to omit real numbers that are not integers. Okay, one more example, then we're done with these identities. I know it gets a little tedious with all these identities. Find the exact value of cosine 15 degrees plus cosine 75 degrees. So that is a sum of two cosine values. So we are going to want to use formula 3, right? And that formula 3 says 2 cosine of 15 plus 75 is 90, divided by 2. Cosine of 15 minus 75, I'm going to write that down, divided by 2. So 2 cosine 45 degrees cosine negative 60 degrees divided by 2 is negative 30 degrees. And then because cosine is even, you get the same result if you just take the cosine of 30 degrees. So this is 2 times square root of 2 over 2 times square root of 3 over 2. So we get square root of 6 over, one of these 2's cancel, 2. Alright, so there's a few examples of where we might use those formulas, especially, I mean, obviously this one you would want to know how to do that on the test, but here, this one, something like that could easily show up on the test. So you have a sum or a difference of a sine and a cosine. You can create a product using the sum to product formula. Okay, well, you can let me know if you have any questions on any of that.